In this video, we're looking at stationary points and the second derivative. So on your screen, you can see a summary of the shape of a curve in relation to the first derivative and the second derivative. So if we're looking at this part here, a graph with this kind of shape has a first derivative that is greater than 0, but also a second derivative that is greater than 0. But if we look down here at this one here, all right, this is showing where you've got a gradient, a first derivative where it's less than 0 and a second derivative where it's also less than 0. So this kind of table can help you identify what the graphs are going to look like in terms of the first and the second derivative. Now if I zoom in down here, here's an important part when solving types of questions. So in essence, if you have a minimum turning point, the first derivative is 0 and the second derivative is greater than 0. You have a maximum turning point where the first derivative is 0, but the second derivative is less than 0. Now for horizontal points of inflection, the first derivative and the second derivative are 0, and there's a concavity change. Now this means that the gradient needs to have the same sign on both sides of that point. So if it's increasing, it's staying as increasing. Now our first question here is to find the stationary point of the curve 3x squared minus 12x plus 7 and show that it is a minimum turning point. So to begin with, I like to write down our function. Now, we do need to find the first and the second derivative here. So let's start with the first derivative. There we go. Now we can use this to find our stationary points in the function. So remember, stationary points occur when the first derivative is equal to 0. So this is how we find our stationary points. So knowing that, we can put this in. We can go 6x minus 12 equals 0. And then we start to find what our x is to find this point. So this cancels out. I'm left with 6x equals 12. Divide by 6 to both sides. And I get x equals 2. So I know there's a stationary point when x equals 2. Now, I should find the y point because, again, this is a point, so we need to know what our x and y value is. So if I go back to my original function and change all the x's to 2. So again, I'm looking at this function here, and what I'm doing is I'm changing all the x's to 2. So I get f bracket 2 bracket equals 3 times 2 squared minus 12 times 2 plus 7, and that comes out as negative 5 if you use a calculator. So I know our point is going to be at 2, negative 5. The next thing I need to determine is what kind of point it is. We need to show that it's a minimum, but to do this we work with our second derivative. So we need to find what our second derivative is. So before I do that, we should probably write down what the first derivative is. Now the first derivative, if you remember, was 6x minus 12. So let's differentiate that, and we get 6. Now remember, in terms of your second derivative, since my second derivative here is greater than 0, this means we have a minimum turning point. All right, and that's just showed us that this point, the stationary point we have at 2, negative 5, is a minimum point because the second derivative is always greater than 0. Now let's look at our second question. Show that 2x cubed minus 5 has a horizontal point of inflection and find its coordinates. So again, we kind of start the same way. Fx equals 2x cubed minus 5. The first derivative is going to be 6x squared. And while I'm here, let's do the second derivative. The second derivative is going to be 12x. So we're going to go back to focus on the first derivative because we always need to find our stationary points first. So again, we want to show we need this for our stationary point. So let's go ahead and do that. So we're saying that 6x squared must equal 0. We can divide by 6, but 0 divided by 6 is still 0. Then we can square root both sides and we get 0. Okay, so we know there's a stationary point when x equals 0. So let's go and find what my y value is. And again, you're just substituting 0 back into the original equation. And I end up with minus 5. So the coordinate is going to be 0, minus 5 for this stationary point. So now we need to determine what's happening in terms of our concavity to the left, middle, like the left at this point, and what's happening to the right. So to do that, I'm going to write down my table. So I know there's, let's do it in a different color. We have our x values, we have our second derivative, and then we have our signs. All right. So in terms of this, we're using, to find these, we're using this here, our second derivative. So I go down here. I want to pick a point, an x value to the left. So let's say minus 1. We have our stationary point and we have a point to the right. So if I go back and substitute in -1 into my second derivative, I get -12. We get 0 here and we get 12 here. So we go from a negative to a positive, so there is a change in our concavity. So therefore, this is a horizontal point of inflection. Now, if we go down here to the next question, we need to find any stationary points on the curve, x to the power of 4 plus 8x cubed plus 16x squared minus 1, and determine whether these are maximum, minimums, or what kind of points they are. So we start the exact same way we started every other one. You write out your function. We find the first derivative. Let's find our second while we're here. Alright, so now that we've got each of these, we go back to the first derivative, and remember, we find our stationary points. And remember, stationary points occur when that first derivative equals 0. So knowing that, we can write 4x to the power of 3 plus 24x squared plus 32x equals 0. So I notice we have a 4, a 24, and a 32, so I know there's a highest common factor in there. Just so happens to be 4, so we're going to divide everything by 4. So we get x cubed plus 6x squared plus 8x equals 0. I can then look to factorize some things down. I notice each one of these has an x, so I can bring the x out the front, and I get x squared plus 6x plus 8, which is a quadratic. So if I factorize a quadratic, then you can use whatever method you prefer. If you want to use the quadratic formula, you can do that. I'm not going to do it on this video to save some time. So we get x bracket x plus 4 and then x plus 2 equals 0. So in terms of this, we know our front x here needs to be 0. The x inside the first bracket needs to be minus 4. And then this x out here needs to be minus 2. Alright, so we know there's stationary points at each of these. Now, pick one of them to focus on and we'll find everything we need to do about that first, and then we go to the next one. So I'm going to start with the 0 one. So let's focus on x equals 0. Just add some structure to our working out now. So now that we do this, we want to find what our y value is. So we're going to go back to the original equation, change all the x's to 0. So we get 0 to the power of 4 plus 8 times 0 cubed plus 16 times 0 squared minus 1. So we get minus 1. So we have our point is going to be at 0 minus 1. The next thing we need to determine is our second derivative. Now, if you remember, that was 12x squared plus 48x plus 32. Now, we're changing all the x's to 0. So we get 12 times 0 squared plus 48 times 0 plus 32, which equals 32. So because our second derivative, this 0 here, is greater than 0, we know we have a minimum turning point. Now, if you don't remember these, remember you can always go back in the video, or if you've written down your notes, have a look at what we said there, how to determine what a minimum and a maximum turning point is. So if it's bigger than 0, minimum, less than 0, maximum. All right, so now that we've done that, we need to do the exact same thing for all the other x values we found. Now, I'm not going to write out every step, but I will show you the answers. So let x equal -4. So let's do that one first. Right, and I want to find my y value, so -4, and that ends up being -1. Again, I'm not going to do all the working because it's just what we did just previously. My second derivative here came out as 32, and what that means is because my f -4 is greater than 0, we have a minimum turning point here. So again, we just do the exact same. So let x equal -2. We're going to focus on our -2 now. And we say, well, what's my y value at this point? So let's substitute the -2 into the original equation. We get 15. We then find our second derivative when x is -2, and that ends up being -40. So what that means is if my second derivative here is less than 0, we have a maximum turning point. So to recap the core principles of what we did today is we looked at the minimum turning points and we said, well, if you have a first derivative that's 0, but the second derivative is greater than 0, that's a minimum. If you have the first derivative as 0, but the second derivative is less than 0, that's a maximum turning point. When they are the same, both as 0, we know we have a horizontal point of inflection when the concavity changes.